Okay, so number 10. There's a lot going on with number 10. First of all, you have to realize they give the diameter of the flywheel. You want the radius, so 0.60 meters. And they tell us that it has an initial angular speed of 200 revolutions per minute or every 60 seconds. So I'm going to go ahead and get rid of the minute. I'm going to take it to nothing yet. Part A wants to know what is this 200 revolutions every 60 seconds in radians per second. So 200 revs every 60 seconds. And there are 2 pi rads for every 1 revolution. So those cancel. So now I have 400 pi radians divided by 60 seconds. So when I did that, I got 20.94 radians per second. Okay, part B wants me to convert that into a linear velocity. So tangential linear velocity is equal to omega r. So I had 20.94 radians per second. And I'm going to multiply that by 0.60 meters. And when I did that, I got 12.6 meters per second was my tangential velocity. Part C said, what is the constant angular acceleration in revolutions per second squared if I'm going to increase the speed to 1,000 RPMs, and I'm going to take 60 seconds to do that. So I'm going to say alpha is change in omega over change in time. So it went from 200 revolutions every 60 seconds to 1,000 revolutions every 60 seconds. So I'm going to say omega F is 1,000 revolutions every 60 seconds minus 200 revolutions every 60 seconds. And that's going to get divided by the time, and the time was 60 seconds. Yep, it took me 60 seconds to make this happen. So when I did that, I got alpha to be 0.22 revolutions per second squared. Revolutions per second squared. And it was positive because we were speeding it up. Alright, then I believe there was a part D. Okay, and part D said how many revolutions will it make during that 60 seconds. So theta is equal to 1/2 alpha t squared plus omega it. So that's 1/2 0.22 revolutions per second squared times 60 seconds. Don't forget to square it. Plus omega I. Omega I was my 200 revolutions every 60 seconds, which is, let me think about that, 60 will go into 200. What did I have? 3 1/3 revolutions per second. And I'm going to turn that for 60 seconds. So I did all that math, and when I did all that math, I got 600 revolutions. Okay, let's move on to number 11. Number 11 has a man standing on a bar for some odd reason. Okay, so here's what I know. This is like the wall. Boy, that's a sad looking diagram. This is 67 degrees. Here's my little man. Okay, now it tells me that the whole bar is 5.2 meters. And from here to here is 1.25 meters. So this is a torque problem, and what they want to know is they want to know, first of all, they want to tell me that the beam itself weighs 288 newtons. Well, if it's a uniform beam, then right in the middle there's a weight of 288 newtons. And then they tell me that the man weighs 75 kilograms is his mass, so I converted that kilograms into newtons. And let me see, that was 735 newtons. So his weight is right here, and it's 735 newtons. Alright, so I got all of that so far. And then they said, oh, you know what, I think I'm doing number 12 instead of number 11. I apologize. We'll go back and do 11 in a minute. Okay. So then they said, what is the weight of the man? Well, we just found that. W equals mg. So 75 kilograms times gravity gives me that weight of 735. And then part B said, and again I'm working number 12 and not number 11, I apologize. Part B said, what is the tension in the cable? So what is that right there? Well, not real hard to get. Just imagine this tension is really made up of a Ty component and a Tx. Not worried about Tx because I'm going to put my pivot point here. And if I put my pivot point there, this force won't be able to make this bar rotate. The only thing that's going to rotate it is Ty. So if I follow a rotation caused by Ty, it's going to rotate like that. That is a clockwise rotation. This weight is going to make it fall in that direction. His weight is going to make it fall in that direction. If I cut that string, it would fall like that. So these two forces are going to create what we call counterclockwise torques. Come on, little pen. Alright, now because I have equilibrium right now, when it's all tied up, I know that my clockwise torque has to be balanced by my counterclockwise torque. So my clockwise torque is going to be Ty, and Ty is going to act from the end of the rod all the way over to here, so that's 5.2 meters. And then I have his weight, 735 newtons, and the torque arm for his weight is 1.25 meters. And then I have the weight of the bar, 288 newtons, and its weight is right in the middle. So from here over to here is 2.60 meters, because half of 5.2 is 2.6. So I'm going to multiply this times this, add them up, and then divide by 520. And that will give me my Ty. So when I did that, I got Ty to be 320.7 newtons. But that's not what they're asking me for. They're asking me for T. Well, I have a triangle. If this is 67, this is 23, if I remember correctly. So I can say the cosine of 23 degrees is equal to Ty over T. Or T is equal to Ty divided by the cosine of 23. So 320.7 newtons divided by the cosine of 23. And when I did that, I got the tension to be 348 newtons. Alright, so I'm going to stop and start another one.